I don't know why it started doing that. So, afternoon all. We're going to move on to the last part of thermal physics since we already did gas laws. We did heat transfer on the video. We did linear expansion and the kinetic theory. So we just have the last bit to do, which is the heat energy, which is, honestly, the most applicable part because heat is a measure of energy. And we're going to ask, when are we getting to the point where we calculate the energy? That's what we're going to do today. So you're going to look at energy. This is where most of the maths is because gas laws was only one equation that you played around with. Here we're going to have um, essentially two equations, but we have four versions of it. All right, so let's go on to it and move forward. Oops, sorry. I still don't know why it scrolls up by itself. So let's read from the screen. I think I did post up the handout quite a while ago on the Google Classroom, so I hope you all have it printed. So reading from the screen, folks. When an object absorbs heat, we can determine how much heat it absorbs by looking at the material itself. Each material has a specific affinity for heat absorption and loss. And as a result, we're going to look at two properties. We're going to look at heat capacity and then specific heat capacity. One is a really broad, wide term. It really isn't too specific, right? It's not that accurate or detailed or precise, hence why they have the proper one that we use in most of our calculations, which will be specific heat capacity. Both of them are extremely similar together to each other, I mean, but one is a lot more exam user-friendly or product user-friendly and whatnot. It tells us far more information than the next one. So let's go into heat capacity. Remember, this is heat energy, so we're going to be using topics to work with heat energy and the energy involved with heat. Trying to get a good one. Right. So heat capacity tells us how much energy is gained when we raise the temperature by 1 degree Celsius or 1 Kelvin. So yeah, that sounds like a maths question, like an equation. So I have energy is equal to, marker is too thin, right? Energy is equal to my change in temperature, delta T. Remember, delta here is a math symbol that represents change. And delta T will be your temperature multiplied by a constant called heat capacity. All right, so you're usually going to see this in two forms. You're either going to see it as E delta T by C, or E is equal to delta theta by C, where we use theta to represent our temperature. This is the more preferred way you will ever see this equation, using delta theta, but both of them mean the exact same thing. Delta just simply means that we look at how much energy it takes to move from one temperature to another one, which makes sense because heat is a measure of energy. And if we are changing the amount of energy in a system, obviously the amount of heat is either going to get bigger or smaller. The very first note we have from thermal physics, heat is our first indication of either too much energy or too little bit of energy. Nothing else tells us about energy presence more than heat. All right, so we have here E is thermal energy, delta theta is your change in temperature, and C is your heat capacity. The unit for heat capacity is kilograms per joule. Now here we just did gas laws, and gas laws told us that we must use temperature must be measured in Kelvin. The way gas laws works out, if we don't use Kelvin, this will not work. But when it comes to energy, you're going to realize that it doesn't matter whether we use Celsius or Kelvin. So I'm going to save you some trouble. We're going to look at that right now before we go into the rest of the topic. Temperature change. Kelvin is a temperature scale widely used in physics. Correct. We just did that in gas laws where we had to go and use Kelvin to do your calculation. But when it comes to temperature change, it makes absolutely no difference whether or not we use Kelvin or Celsius. You all get your calculators out fast. We're going to try something and see. All right, so let's think about it. Even though it's written on the board here, all right, everybody, if my temperature starts from 10 degrees Celsius and it goes to 15 degrees Celsius, mental, what is my change in temperature? I know it's real obvious and simple. In Celsius, if my temperature went from 10 to 15, what was my change?
5 degrees.
5 degrees, right? Now we want to see how how we can make the statement that it makes no difference whether or not we use Kelvin or Celsius when we look at temperature change. Y'all, how do we convert Celsius to Kelvin again? Somebody tell me. We add how much?
273.
273. So you all tell me right now, if my temperature is 10 Celsius, what is it in Kelvin?
283.
283, right? And if my temperature is 15 degrees Celsius, what is it in Kelvin?
288.
288 Kelvin. What's the difference in these two numbers?
5 Kelvin.
Still 5 Kelvin, right? So you see, when it comes to looking at change in temperature, where we have to take one number and subtract the next one, it really doesn't matter whether we use Kelvin or Celsius. It's because um, we just add in a number to our value. That's why our difference is not going to play a factor in our delta theta. Delta theta here means one temperature minus another one. All right, so here you all can see it does not matter whether we use Celsius or Kelvin. So it is completely unnecessary, folks, to convert to Kelvin for heat energy questions. Saying it again, it is completely unnecessary. You don't have to do it unless they tell you to, right? But you don't have to convert to Kelvin when you have to do heat energy questions. Why? Because we're subtracting one number from our next and it makes no difference. All right, so saving ourselves from a little bit of trouble. Continue reading. Specific heat capacity. Reading, heat capacity is not a very accurate term. It does not tell us how much material can be heated, nor how well a material will hold on to heat. What was heat capacity equation? Heat capacity equation, scrolling back up, was E is equal to change in temperature by a constant. But let's use some common sense here. If I have a small little spoon, let's think about a little spoon that you all have. That's not a spoon. All right, our pot spoon that we put into our pot. All right, let it get a little space, a little handle in our spoon. All right, so suppose we have a little pot spoon, all right, and we put that in, say, like a hot pot of water or whatnot. That's gonna heat up pretty quickly, all right? But suppose you all go and get one of those big, huge, heavy spoons, or you can get a heavy knife and you put it into a pot of water. It's gonna take a longer time. Oh, that's why I'm not drawing. It's going to take a longer time for draw, right? For a big spoon to get hotter than a small spoon. Let's say you take a regular soup, a little tiny little spoon that you all use to do teaspoon. Which one is going to get hotter fast, the teaspoon or your big pot spoon?
Teaspoon.
The teaspoon, right? Even though they're made out of the same material, right? If you all get a thin little small pot, right, like the saucepan we use on the fire, right, that we use to make tea in the morning. I hope you all use a saucepan and not a microwave. That's just wrong, right? When you have a saucepan on the fire in the morning, right, this gets hot pretty quickly. As in, by the time you turn, go to the bathroom, come back, not to bathe, I'll go to the bathroom, pick up your clothes, get something. This water is boiling. But say you all go and get the same water. You get one of them big heavy pot that you always make pilau in. You know, we use the big heavy pot to make pilau in, all right? Not a tin light pot. All right, big heavy pot. And we put that same amount of water in it. Will this water boil as fast as the little tin pot? Anybody?
It will
No.
take longer.
It'll take longer. Why? Because the mass of your pot makes a difference. If you use a thin pot, right, a thin light pot, that's going to heat up in no time. But when you use a big, heavy, thick pot, right, you're going to take a longer time to heat up something. It's going to take a longer time to heat up. And flip side, if you all take this really thin pot that you all boil water with in the morning, right? You go to the bathroom, you bathe, you change your clothes, and come back. And that pot is pretty cool. You could lift it, take it and put it to wash and everything, right? It's pretty cool. But you take that big heavy pot that you made pilau with, or big curry chicken with, and go bathe the same amount of time and come back. That pot is still really hot. Why? Because how much material here determines one, how long it takes to heat up, and flip side, how long it takes to cool down, right? And what makes a difference is the type of material, the material is the apparatus or device is made out of, and how heavy it is. Because we know something that is heavy is going to take a long time to heat up, and flip side is going to take a long time to cool down. We could even go on the next flip side. We know something that is really light heats up very fast and it cools down extremely fast. So heat capacity takes no consideration, makes no consideration for mass. And mass is an extremely important topic when it comes to energy. Right? So this is where we have, so that's why we say heat capacity is not the most accurate of term. It's a really vague term if you want to work with something quickly, right? But it's not the preferred method because you're leaving out a very important part. So instead of heat capacity, we use something more specific, hence the word specific, right? We use specific heat capacity. So this is where we're actually honing into an actual value or something really finite, and we can look at how each individual material behaves differently. So what is the definition of heat capacity? Heat capacity, the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of object by 1 kilogram by 1 Kelvin. So if you put this in the formula, right, you're going to get energy is equal to mass by specific heat capacity, which is a capital C, right? Not an E, that's actually a C. Let me write it properly. By capital C by your change in temperature. And here we can actually take into consideration, we know the heavier something is, the more energy it will have. Meaning the more energy it will take to heat up and the more energy it will hold on to or to cool down. Right? Specific heat capacity is a constant. The nice about specific heat capacity, there's something that we call a characteristic property. Characteristic properties are things that we use to help define our material. And anything that we need to know about the melting point and boiling point, or if we have to use it in thermal physics and engineering, we need to know how much heat it can hold. Right? And this goes straight back to the structural engineering and the linear physics, the linear expansion that we did. Materials that expand more have a higher heat capacity, right? Materials that don't expand too much have a lower heat capacity, right? And we have to learn to use the heat capacities to work out how our material behaves. So this is why we have all of these topics put together, because there's numerous amount of properties that we need to consider when we're doing our calculations. So energy, We refine our energy equation, mass by specific heat capacity by our change in temperature. Because obviously, how hot we change, how hot we heat up something or how cool we make it determines how much energy we have gained or we have lost. All right, so here, please note our units. Energy is always measured in joules. Doesn't matter what type of energy. It could be thermal energy, it could be electrical energy, it could be mechanical energy, it could be nuclear energy. They're all measured in joules. Mass is always measured in kilograms. So you all are going to have to be careful when you have to convert from grams to kilograms. That's to revise, because we're always going to revise. Write it down, because I don't want anybody telling me nonsense. Right? When I have to go from grams to kilograms, when you need to convert from grams to kilograms, you divide by, let me see if anybody can make me proud this evening. Prouder this evening. How much we have to divide from grams to kilograms? Anybody know how many grams in a kilogram?
1,000.
8,000. Right? So it's 1,000. So anytime you all have to go from grams to kilograms, please, please divide by 1,000. And even better yet, use standard form when you can. If you realize you're going to get more than 2 decimal places for a small number, folks, use standard form. Right? It makes it easier to calculate, easier to write down, easier to keep track of. Continue reading. Specific heat capacity, the units for specific heat capacity, or as I call it, SHC, specific heat capacity, is joules per kilogram per Kelvin. Anytime you have something that has the power -1, we call it per that topic, right? So if I have per kilogram to the -1, we call it per kilogram. If I have seconds to the -1, I call it per second. That is how we say it, right? We have to learn how to say our things properly. You don't come and say joules or J, kg to the -1, k to the minus. No, no, no. That's for non-physics people. Let's say these things right. Okay. If you want to, let's look at how we get the units of this unit of the units of this quantity. So make sure and write this down here, folks. Ladies and gents, please write down this value. If I have energy is equal, we want to see how we get the unit for specific heat capacity. So my energy is equal to mass by specific heat capacity by my change in temperature. If I make C the subject of the formula, or I transpose my formula, I'm going to get C. Remember, anytime I want to get rid of something that's being multiplied by a term, I divide by that same term, right? So C will be E divided by mass by change in temperature. And if we put our units, what are the units of energy? Joules divided by what is the unit of mass? Kilograms. And what is the unit of temperature? It will be Kelvin, because we still are using Kelvin. Remember, we said it's not necessary to do the conversion, but the temperature scale still is going to be in Kelvin. So I have joules over kilograms by Kelvin. And the way we see it is we write it down. It's going to be joules per kilogram per Kelvin. So that's what this means. Y'all, we get marks for using our units accurately. All right, so please use your units properly when you can. Further on, that's for the mathematics' sake. When a system is being heated, you'll hear the song in the background? On early.
We just saying yes.
Okay, good. Because it sounds really loud to me. Okay. All right. When a system is being heated, our delta theta, or change in temperature, is going to be positive. Why is it positive? Because when we heat something, we start at a small temperature and we go to a higher temperature. Correct? You okay? Give me thumbs up, or it's a yes or no. Good. All right, so when we heat something, let's just check. All right, so I'm running through all the little fine points right now. When we heating something. All right, let's use an example. I say I'm going from, say, 10 degrees to 50 degrees. Yeah, we're heating it up, all right, because we're going to go from cooler to hotter. And if I were to find my change in temperature, my change in temperature is always my final temperature minus my initial temperature. Let's get it right because children get this wrong sometimes. The numbers in this topic make a difference. The signs make a difference. Positive indicates heating, negative indicates cooling. So if you all start getting negative signs, you have to better make sure you all are dealing with the right conditions. So when something is being heated up, our delta theta will be a positive number. How do you know to calculate the delta theta? Delta theta is your final temperature, which is theta F, theta final, minus theta I, which is theta initial. Initial is your first, F is your final. All right, so in this case, it will be 50 minus 10, and this is going to give you a positive 40. Everybody okay with that, right? Yeah. Let's look at cooling. All right, now when we are cooling something down, we say when a system or material is being cooled, delta theta will be negative. All right, so anytime this is where the sign makes a difference. The sign tells us what is happening. So we can't do our calculations incorrectly, which is our simple arithmetic. We can't do it incorrectly because we're going to get the wrong answer. All right, so if I had, let's use an X marker. Suppose for something, if I'm cooling it down, say I had 100 degrees Celsius tea, or very hot tea in the morning, and we want to cool it down till it reaches a temperature that is nice and, drinkable. You can drink tea when it's 40 degrees Celsius. All right, so here if I wanted to work out delta theta, all right, it's going to be our final temperature, which is where we ended up at, and theta initial, which is where we started from. It's never always the bigger number minus the smallest number. Everybody, do not make that assumption. You are shooting yourself in the foot if you make the assumption, oh yeah, it's always a big number minus a small number. Please, pretty please don't do that. Read your question properly. Delta theta is your final temperature, which is your last temperature, minus your initial temperature. And when it comes to the topic of thermal physics, we do two things. We can heat something up or we could cool it down. So where we start from and when we end up at makes a difference. So here our final temperature would have been 40, our initial temperature was 100, and you're going to get minus 60. So this is why I said when something has a positive delta theta, it indicates that we're heating it up. And when it has a negative delta theta, that means we're cooling it down. The negative indicate that we took heat out of the system, and by taking heat out of the system, we've cooled it down. Physics, common sense. When you think about it, well, yeah, that makes sense. If I add heat, it'll get hotter. If I take away heat, I'll cool it down. Latent heats. State change. You all, what are the three states of matter? Physics, chemistry students, both, you all are both.
Solid, liquids, and gas.
Solid, liquids, and gas. And that is what we call, whenever we move from one state to another, we call that a state change. And we have a whole set of state changes that can happen. All right, so let's look. We have solid. Oops, wrong marker. I have solid, I have liquid, and I have gas. All right. Somebody else answer me because I want to hear everybody from the class. Malika, if you want to answer, you can put it in the chat so I still know that you're answering. Don't worry. When I go from solid to liquid, what am I doing to that material?
Melting.
Good, melting. When I go from liquid to gas, somebody else, what am I doing?
Vaporizing.
Vaporizing. Good. And I love that you use the word vaporizing and not evaporating, right? These are two little different terms. Let's look and see. What happens when I go from liquid to solid? What process is that?
Freezing.
Freezing. I love it. Sounding good. When I go from gas to liquid, what process is that?
Which I think is condensation.
Condensation would be correct. And for bonus points, when I go from solid to gas, what we call that? Starts with S. U, B,
Sublimation.
sublimation. Right, that's our bonus one. So we do have the case of when something goes from solid to gas, and that's to sublimate a material. We don't ever look at sublimation calculation, straight calculation in physics. We always just look at these transformations. All right, that's what the topic here, latent heat. This is when we make state changes. State changes is when we, let's look at our different state changes. We can melt, we can vaporize, we can freeze, and we can boil, or we can just heat something up. We can get we can get a solid and we can go from theta 1 to theta 2. We can heat up a solid. We can heat up a liquid, right? We can heat up a liquid from one temperature to another, right? Similar, we could cool it down. All right, but then we have our particular points where we change our states. Now, something specific happens at a state change. What's the most important thing that happens at state change? Our bonds change. The nature of our bonds between molecules, not inside of molecules, the nature of our bonds between the molecules change. So that means we need extra energy. Our energy is used differently when we have to undergo a state change. You also see this is why it's really nice to do chemistry and physics together, because one explains how the other one, or at least it exposes you to both sides of the coin. So let's read from the handout. When a material undergoes a state change, it does so at a constant temperature and without the use of external heat. The energy use or the energy to break or form bonds for a state change come from within the material and the atoms itself. For an atom to become a liquid, the vibrational energy that's held within the atoms are used to convert, or that's not two, are used to convert or break some of the bonds to turn it into liquid. Because remember, let's think about solid to liquid water. We went into why water gets larger when it freezes, because we took our little bendy water bonds and turned them into straight solid bonds. And the energy in a solid material, remember, the energy in a solid material is a lot of energy, because the molecules now are constantly vibrating. Because they're constantly vibrating, right? If you give them enough energy, they have enough energy stored in them already to break those bonds. That's how it works as a solid. You just have to give them enough energy to reach a particular point, and the molecules will say, you know what, I have this, I'll do the rest myself. And that's what happens. You give a material enough energy till it reaches a certain point, and at that point, the molecules can do the rest of the job, which is to change our state. Um, so let's read. This only happens when a material reaches its melting point. That's to go from solid to liquid. From solid to liquid is called melting. At this point, the molecules have enough energy to break its bonds without any further heating. So this is what we said. We've given the bonds enough energy, and when they've gotten enough energy to a certain point, it's like, we can do the rest of the breaking right now. We good to go. We could go and turn this into liquid right now. A similar procedure happens when the material makes the transition from liquid to gas. When we go from liquid to gas, we have to heat up those liquid molecules, give them enough energy till they reach a point where they can break all those liquid molecules, liquid bonds, and become gaseous. And then there's the flip side. When we have a gas, if we pull out enough energy from that gas, right, we prevent those molecules from moving around too much and they will bounce into each other more and more because they have less energy, right? And then they could form bonds. Similarly, for water, right? No, for not for water, just for freezing a liquid. When we take out heat from a liquid, right? We take those flexy, bendy bonds because they're always in motion. If you look at the video, always in motion. And when we take out energy, they're going to move less and less till they reach a point of forming a nice straight bond. All right. And when they form that bond, that's the molecules themselves doing the job. We have added the heat, or heat has been added to the system until it's gotten enough for it to make a change. So let's continue reading. We look at the graph just now. The energy that comes from within the material itself, the energy comes from within the material itself and is therefore called latent or hidden heat. Latent means hidden. And why we call it hidden? Because it actually comes from within the material itself. If we're heating up something, we're doing this externally. We can do it by a flame, we could put it in a hot oven, or you could put it in a cooler or freezer. That is external. But anytime a bond has to break, that means that the bonds from inside of the material are breaking or forming. We can't see when that happens, so that's why we call it latent heat, right? Because we can't see it and we are not applying, meaning the change that is being done to cause that bond or that transition. So we have latent heats, right? We have a few types of latent heats, right? A latent heat is simply the heat required to change a bond, right? Heat or energy required to change a bond. So let's look at the different types of heats, latent heats we have. We have latent heat of fusion. Fusion here is the kind of energy we take to go from solid to liquid and backwards, liquid to solid. We're going to say why those are the same 2 points just now. And then we have the next one of latent heat of vaporization is where we go from a liquid to gas or gas to liquid. And the English is going to tell you what it means. Fusion means to fuse together. And when I fuse to something together, I'm going to get, rather than get a liquid, you're going to get something more concrete or something more stable. You fusing stuff together. Vaporization, well, that's obvious, right? So let's read and see what's happening here. Then we're going to go to the graph to explain the graph. Solid to liquid. Now, this is where students have to realize that two terms mean the same thing, right? When a solid turns into liquid, it has reached its melting point. Yeah, that makes sense. All right, let me just blow your minds a little bit here. When I say something is melting, don't you all assume that it's hot? We're using common sense, real world application. If I say something has melted, don't you assume that it's in a hot situation?
Yes.
Yeah? We're not talking about physics right now. That's, from what you've known all your life hearing it. Yeah, when I melt something, obviously it has to be hot. And when I say I freeze something, doesn't that mean it's gotten cold? Yep. Anytime I say something is freezing, or I freeze an object, or I freeze something, mean I turn it into a solid, I assume that it's cold. But freezing point and melting points are the exact same thing. Why are we saying one is hot and the next one is cool? It comes from the straight explanation for heat movement. When I melt something, that means that we assume it's getting hot. Why? Because we're adding heat to it. In order for something to melt, we have to add heat to it. When we add heat, this is where we get the conception or is it word conception? The impression that we are heating it up or getting hotter. When we freeze something, we have to take heat away from it. And anytime we take heat away from something, we assume that it's getting cool. But folks, both melting and freezing points for every single material is the exact same temperature. Let's think about it in terms of water and ice. This is our solid and liquid. At what temperature does water freeze at? 0 degrees Celsius, right? Water freezes at 0 degrees Celsius. And at what temperature does ice start to melt? 0 degrees Celsius. Ice starts to melt at 0 degrees Celsius. And this is where ice starts to melt. Ice is the solid form of water, and ice begins to melt at 0 degrees Celsius. So here we can see that both melting and freezing points of a material at the exact same point. We just assumed that we were talking about hot and cold because we didn't really identify that hot meant we were adding heat and cold meant we were taking away heat from a system. When you take away heat from a system, we cool it down. Cooling down doesn't mean that it's cold. I'm going to use a little bit of math sense, right? I can't tell you the melting and freezing point of iron, you know. If we get the melting point of iron, melting point of steel, okay, we can take steel. All right, steel melts at say 1400 degrees Celsius, 1450 degrees Celsius. Steel will turn into liquid, molten steel, that hot material, that hot liquid that will melt off your skin and worse. It will melt at 1450 degrees Celsius. But guess what's going to happen? Suppose I have steel and I've heated up further to 1500 degrees Celsius, and now I let it cool down and say it's now 1400 and say 45 degrees Celsius. Just under. What's going to happen to my steel when it moves from 1500 degrees Celsius to 1445? It has lost heat and it's now going to start to turn to a solid. And anytime, according to the definition of liquid to solid, anytime a material goes from liquid to solid, it freezes. Freezing has nothing to do with getting cold. Freezing simply has to mean that we have turned our liquid bonds into solid bonds. We kind of making saying life is a lie right now, right? I hope you're feeling like life has been lying to you. Because when we make such generalized terms, right, we realize, oh, okay, freezing points and melting points, exact same temperature. They mean the exact same thing. And likewise, we have for boiling and vaporization and condensation, right? If I have a material, not the freezing, the vaporizing point is equal to the condensation point. Right? Because the temperature at which a liquid will condense and become the temperature at which a gas will condense and become a liquid starts at the exact same temperature that it turns into a gas. That's the exact point where it could either go forward or back. We can either go forward and turn into gas, or we take our gas and turn it back into a liquid. But remember, gases are a little different. We don't tend to work with gas too much in heat energies because looking at the gas laws, you realize that it has too many components. So mainly here, we always look at solids and liquids. We already had a whole topic on gases. Let them go so. All right, so let's look at our graph as we had at the top here. This graph is what we call our state change graph. You all have to know how to identify and explain this graph. So let's look at it. You all can get this graph in two different directions. You can get a graph looking like this, where this is your heating graph, and we're going to look at what the cooling graph looks like, because we didn't do it in class in school because we already did enough heat labs, but we should have done this lab in school if it wasn't for COVID, of course. All right, so let's think. We start at a metal. This is time and this is temperature. And when something is solid, it is technically cold. Cold doesn't mean it's low down in temperature. Low down as in 0 degrees, minus 10 degrees. Cold means that it's where our bonds now exist in a solid configuration. Right? So when I start to heat up, so as time goes by and I start to heat up my solid, the temperature is going to change as time goes by. We can understand this graph very easily. Right? As time passes, our temperature is going to increase. Say we're heating up our solid. Now it's going to reach a specific point where it has now reached its melting point. When it has reached its melting point, it's no longer going to absorb heat to change its temperature. What it's going to do now, if it has any extra heat in the system, it's going to use that heat, not for temperature change, but for state change. So once a material, I was not going to say liquid, once a material has reached its melting point, and a melting point is a specific point for every single material. Once it reaches that melting point, it takes that energy and converts it, uses it to convert its solid bonds into liquid bonds. So here we're using the energy for something different. Before we were using the energy to just heat up the system for it to get hotter. But once we reach our specific point of melting point, we are not going to use that temperature. We're not going to use that heat to change our temperature. Heat here is a measure of energy. This is where people have to, break out of our regular cycle of terms that we've learned for our entire lives, right? Heat means energy. And all our energy right now, they're not being used to heat up the system. They're going to be used to break our bonds. So at this point here, this is what we call our state change, and it's usually a flat curve. It's a flat point in our curve where our temperature stays constant for a while. Why does it stay constant for a while? Because number one, it's not going to get any hotter, it's not going to get any cooler, because it's going to use any heat available to break bonds. All right, and this is what we call our solid to liquid mixture. So as time goes by, we're going to get less solid and more liquid. So more of our solid is going to melt, and when it has melted, we are now fully liquid. Now, once I have a liquid, I can heat up my liquid. So just as we did before, as time goes by, my liquid is going to get hotter and hotter. And then it reaches a next specific point. What specific point is this? This is where our water now can reach its boiling point and start to vaporize. Right? We know something has to be really hot when it starts to boil. Something different happens to material when it starts to boil. Boiling, and when it does that rapid bubble, when it starts to undergo rapid convection currents, that's boiling. And at boiling point, we are going to have that same flatten out of our curve. So we had a nice curve going up, then we're going to flat out, and then we're going to go up again, and then we're going to flatten out again. This flattening curve now means that any extra heat that's being added to the system, heat meaning energy, any extra energy that's being added to the system are being used to break those liquid bonds to become gaseous molecules. So that's why we have this flat curve, because we're using the energy to do something else. That energy is to break bonds. Before, we were just using it, you know, to add more energy or to heat up our system. Here, we're using the energy to do something specific. Then we're going to get, our liquid is going to vaporize more and more and more until we have no more liquid and we end up only with gas. And you can just heat up your gas until it reaches a certain point. All right, all gases can be heated to a point until we break down the molecules. And that's a really big temperature. right? Really, really, really big temperature. So we don't go on to that point. So this is our heating curve. Now, you very rarely get the heating curve in exams. You tend to get the cooling curve, all right? And the cooling curve would have been a lab that normally we do in school, but COVID things now. So let's look at what our cooling curve is supposed to look like. All right, so our cooling curve, again, x-axis is always time. Now you can measure time in seconds, in minutes or hours. It depends on your material. Your temperature. So let's say I start with something that's, I have hot gas, right? And now I'm going to start cooling down that hot gas, right? So that gas is going to cool down, right? I'm going to cool down that gas until it reaches a point. So this is my gas. Until it reaches a point where I have pulled out enough energy from my gas to, the molecules going to come closer together. They're going to bounce into each other. And now they're going to start forming bonds and become a liquid. So what's happening here? It's not going to cool down any further. All the energy that's being pulled out of it are going to be used to form liquid bond. So this is where we're going to have the state change of gas to liquid. So now we've reached this point where we have only liquid. What happens to our liquid? Our liquid can now go and start to cool down, because as time goes by, you're going to see your temperature is getting smaller and smaller and smaller. Common sense. If you put a hot cup of tea out on the table, after a while, it's going to lose its heat. It's going to get cooler. It's not going to remain hot. And I seriously doubt anybody puts a cup of tea on the table and it gets hotter. Right? You need to call National Geographic if that happens. Something special is going on. Right? So what's going to happen? Our liquid here is going to cool down until it reaches another specific point. What is that specific point? Where we've lost enough energy from our bondy, flexible liquid bonds, and we're now giving them, freezing them, right? Freezing is when we take liquid bonds and we turn them into solid straight bonds. That is the action of freezing. And now we're going to flatten out again, because we are now turning all those flexible, bendy liquid bonds into straight solid bonds. So at this point here is where we'll have another state change. And this state change is liquid to solid. And at this point, as enough time has passed by, right, you all know we start off with water in the freezer when we're making our ice block. And as time goes by, we're going to get a little bit of ice at the top. I'm sure we've done that, trying to pull out the ice tray too early. You get ice at the top, but there's still liquid inside, because not all the liquid has lost its energy. So it takes time for things to happen. It takes time for things to heat up. It takes time for them to cool down. So at this point here, our liquid has now all converted to solid. It's lost all the energy that it needs to be a liquid, and it's going to start cooling down as a solid. So this is what we call our cooling curve. And in a cooling curve, just like a heating curve, anytime you all see a flat part of your graph, flat part, flat, flat part in your graph, that indicates that our material is changing its state. All right, so this is how we're able to read where our material does a state change. And from this graph, we are able to record where our material froze or where our material melted. For a cooling curve, we're going to look at condensation, and we're going to look at freezing. So all you have to do, if you have a cooling curve and you want to read off the freezing point of your material, which is what we would have done in school, we have the material that we use, the chemical that they use to make mothballs, camphor balls, mothballs. It melts at, say, 75 or 72 degrees Celsius. So all we can do, put it into a water bath, boil it, let it melt. And if we just leave it, you can actually see it start turning into a solid pretty quickly. All right, so by the time it reaches 72 degrees, it has frozen. So all you have to do when you're doing anytime you're doing these graphs and you want to read off the freezing point, all you have to do is see the temperature where it flattens out for quite a while. Once it flattens out for a little bit of time, because generally as you go, every time you take a reading, your temperature is supposed to drop. That means cooling. But when you get a flat graph here, that means that the temperature is not changing. So not changing temperature indicates, again, that we're changing our state. So anytime you all have a cooling curve, once it flattens out, you know that is a point, that is a temperature, that that sample, that material that you have right now in front of you, or whatever the question is being referred to, right, that point is where it is freezing. So if anybody has started looking at questions and they give you a graph and say read off the freezing point, it's real simple. Just look to see where it flattens out. So continue going. Okay, so that's it. The time is 2:45. I will give you, I think we'll wrap up there. And I will run a little explanation video on how to do the calculation for freezing and melting and latent heats, how to use them, because I have the entire sequence here. All right, so I'll explain how you can use the sequence further on. It is going to take me more than 15 minutes to do this, all right, because I'll have to go into the next topic. And you all know I don't like to jump between topics. All right, so we will stop here. I can't go and do this right now, but later on, I will make a next little video, just like how we did heat transfer. All right, so I will do a little short video on that. So stop. And just to tell you, even for those in the video, you're going to know where we're moving on to next. We're going to look how to calculate all the energy changes in a material. All right, we're going to look at power, electrical, heat power, and the two methods. This is defined by the syllabus. We have to know the two methods that are used to determine the specific heat capacity of a material. Usually, we will do this lab in class, but not enough time owing to COVID things. All right, but method of mixture is very simple experiment. All right, but you all have to know how to do the two methods, at least in theory. I will probably see if I can get a video, or you can look up videos how to do both. You have to know how to determine a specific heat capacity. We do that by methods of mixtures. All right, so the two methods is not much. And then we have the last bit of topic, which is evaporation and boiling. Evaporation and boiling, again, you're going to realize your life was a lie. It's not exactly as you've been taught. All right, so we're going to finish all that up in the next explanation video. And then we're going to wrap up from there. And after that, which I'll probably put out this week self. And after that, we're going to start doing questions for gas laws. I already have the assignment out for gas laws. We're going to do question on heat, energies, and then we're going to do a big handout or big revision topic on this topic of thermal physics. And from there, that will be our week next week, because next week I should see you twice. Yes, I will see you. No, yeah. No, I won't see you twice next week. Next week has 2 holidays. All right, so I will put out the video. I'll probably put out a next tutorial video. You all can follow it, and we're going to try to cover each topic a week. Folks, ladies and gents, if you all have questions you want me to go through with you, by all means, send them my way. Put them in the WhatsApp chat, or you can send them in a private message in the WhatsApp chat. If you have an issue with a question, circle the part or tell me which part you're getting a problem with, and I will see if I can help you and as quickly as I can. All right, so please send those questions my way. Don't just sit down there on them. Anything you want me to finish or to explain to you, I will see how well I can help you. All right, because that's my job. All right, so you all have a good weekend. Be safe. Continue being safe. All right, and whatnot. Let me stop that share. So you all continue being safe. Mask up, double mask up. You really and truly don't have to go anywhere unless you really have to. All right? Keep studying, send me those questions, and I will see you next week. Bye bye.
Bye, miss.